Welcome to Spring LIB.
So in this question, we already have a large metal plate, parallel plate capacitor with surface area A and distance D, and there is electric field between them. So in part A, what we have is we have a large metal sheet of thickness L, and we put them in between these two parallel plates, and the edge extends out. So we ask now, what is the net capacitance? So in order to solve this problem, we need to start with the definition of how we derived the definition of capacitors. So first, let's find the electric field between them. E equals unit charge over epsilon, which is Q over A epsilon. That is Gauss's law. So usually the voltage difference between them will be E times X. Realize that now X does not equal to D because there is this metal sheet between them. So here, now what happens to X is that this is a conducting sheet. So there will be no electric field inside this, but there will be electric field in these two regions. And these two regions, you can calculate them separately, but we know that when you have two voltage difference, the net voltage difference is the sum of them. So you can just use the sum of these two distances, which is D minus L. And now you find that we know that Q equals C times V. And capacitance is what we're looking for. We have Q divided by V. Q equals EA epsilon. V equals E times D minus L. This is epsilon times A divided by D minus L. Part 2 asks what happens if the thickness of the sheet L equals 0.4 D. By what factor does the capacitance change when the sheet is inserted? So C equals epsilon times A times D minus L is 0.60. So this equals 1.0.6 times epsilon A times D. So this is the original capacitance C naught. This is what the actual factor we have after the sheet is inserted. So this equals 1.6 times this C naught. So what happens is the capacitance of the capacitor will increase by a factor of 1.7.